and A here is an n by n matrix. Lambda is a scalar, and I, which is an identity matrix, it is an n by n matrix as well. So I have this expression. I want to say this for you. Okay, so this is the expression. Now, what can I do? And then here, the important thing is that this x1, x2 is not a zero vector. You have to pay attention to that. It is not a vector which is equal to, not equal to 0, 0. Now, how can I get this equality here? Could you help me in that sense? And what does this imply? This expression here. Bu bize ne söylüyor? Bu matrise baktığınız zaman ne iddiada bulunabilirsiniz? Yani sağ tarafta sıfır vektörü var. Sol tarafta da bir matris çarpımı var aslında. Bu bize ne bilgisi veriyor? Ya da bu ne gösteriyor bize? Can I get feedback from you?
Hocam açıkçası düşünmeye çalışıyorum fakat bir şey gelmiyor aklıma.
Aklıma bir şey gelmiyor.
Evet.
Anyone else who would like to say anything? What basically, whenever this type of expression appears, it tells you that there is something called the key term. Maybe you tell me. Tabii akşamın bu saatinde hepimiz yorgunuz. Ben böyle 3 saattir konuştum bugün. Dedim şimdi tekrar bunu başarabilecek miyim? Evet. Yani aslında ne geliyor aklınıza? Bir bağımlılık oluşturuyor değil mi? X2 ile X1 arasında böyle bir şeye baksanız, şu anda böyle yazdığım için hiçbir çağrışımda bulunmuyor. Ama bunu şöyle yazsaydım, yani oradaki katsayıları kullanmamak için şöyle bir şey yazsaydım ne diyecektiniz? Mesela C1 X1 artı C2 X2 eşittir. Diyelim ki lambda demeyeyim de delta çarpı X1 deseydim. Buradan ne çıkacaktı? Yani şuna bakın ya da şöyle de diyebilirdim. Burada D1 diyeyim. D1 X1 artı D2 X2. Çünkü burada iki tane aslında lineer denklem var. Bunu da mesela X2 yazsaydım. Buradan aklınıza ne gelirdi direkt olarak? Böyle baktığınız zaman. Ne yapıyorum aslında?
Delta aynı zamanda diğer değişkeni de içererek sadece biri üzerinden ifade etmemizi sağlıyor.
Evet, yani aslında bütün yaptığım X2'yi şöyle diyeyim, X1'in bir fonksiyonu olarak açıklıyorum. Tabii bunlar da buradaki her şey doğrusal olduğu için, lineer olduğu için doğrusal bir denklem elde edeceğim. Yani X2, X1'e doğrusal bir denklem olarak ya da doğrusal bir fonksiyon olarak bağlı olarak gösterilecek. Yani yapmaya çalıştığım bu. Ama buna bağlı olarak bir sorun var. Yani bu yaptığımız bu. Bunu böyle açık hani böyle tamam matris şeklinde gözüktüğü zaman çok bir şey nedir onda da hani kafamız karışabiliyor. Ama sürekli olarak böyle bir şey yaratmaya çalışıyoruz. X1 ile X2'yi birbirine bağlı hale getiriyorum aslında. Ve burada da yapılan şey yani hep böyle anlatılır zaten bu vektörler. Şöyle bir vektör varsa, yani eigen value için söylüyorum bunu. Diyelim ki elimizde şöyle bir vektör var. Tabii bu benim çizdiğim gibi değil. It's a line. If there's such a vector, basically they say that with this operation, what you do, you just make this vector shorter or longer, but you all the time move along this vector. Okay, this is what goes on. Somehow this is the geometric description. Given this information, and I know that x1, x2, they are not zero vectors. Yani ikisi birden sıfır olsaydı zaten yapacak hiçbir işimiz yoktu. Onun için x1 ve x2'nin ikisinin birden 0 olduğu durumla ilgilenmiyoruz. İkisi de diyelim ki sıfırdan farklı olsun. Hem x1 değeri hem x2 değeri. Böyle bir durumda, böyle bir durumun olduğunda aslında ne bilgisi de çıkıyor temin yaptığımızdan? Bu matriste satırlar birbiriyle nasıl what can I say about row vectors? Are they independent of each other, those row vectors? In this case?
I think they are not.
They are not, exactly. They are basically linearly dependent, and this is what I have shown earlier. So what does it tell us with those tools that we were playing with? What can I do? Which tools or which tool I can use this fact and then claim that I can find x1 and x2? Basically, here I would use the determinant. If these rows or columns, if they are linearly dependent, that means that this matrices determinant is equal to 0. Exactly. And that helps me to find these lambdas. And when I find those lambdas, basically I can find those x1 and x2 values, which would provide us this equality. Okay? That is the information we get from here. We say that if we establish such a structure, in that structure, we basically make these rows and columns linear, we make them linearly dependent. If there is linear dependence, then this matrix here, this matrix or this matrix, basically means the determinant of that matrix will be equal to 0. And that fact would give me these lambdas. And when I find lambdas, I would easily also, we will solve an example, find those x vectors, okay? And this is the general form, and this is the determinant of the matrix, this matrix here, sorry, this matrix, and it will give me these basically as the roots of this equation, which will be equal to 0, because the determinant is equal to 0. It will give us those the lambdas that provide this. It is called determinantal equation. It will provide us it will give those lambdas, which will give us this determinantal equation. Okay, and those lambdas are called as spectrum of A. Şeyde çok kullanılıyor böyle. If you go deep in time series analysis and look at many different aspects of time series analysis, analytical, let's say, methods, you would hear these terms like spectrum, spectral radius. Basically, it means eigenvalues. The set of eigenvalues are called spectrum, and the spectral radius is the modulus of its eigenvalues, the maximum modulus of its eigenvalues, which means that you take the absolute value of eigenvalues, and the highest one is called the spectral radius. Okay, this is the geometric interpretation. You can read it, but it is as I explained to you. And here, because now we will solve an example, don't worry, this is just a little bit talking about it. Neither eigenvalues nor eigenvectors are necessarily unique. Okay, they are not necessarily all distinct, but when they are distinct, it's good for us. We will see it. It will help us to get certain results quicker. And eigenvectors also can be scaled arbitrarily, since this arbitrary scaling doesn't change anything in terms of the equality that we started with, because we multiply both sides with this gamma, and nothing changes. So we can scale those eigenvectors as we want. And here the numerical example of how we find these eigenvalues. Now this is the matrix that we would be dealing with, okay? And in order to, we are after this equation, okay? And this is the A matrix. And we said that we would look at this one. Let me write for you. A minus, this is the matrix that we are interested in, I, okay? I didn't write the dimensions, but you can guess it. And we are interested in the determinant of this matrix. Right? And here, because if I write it in this way, let me say, this is the matrix that I'm interested in, 4, 3, 5, minus lambda, 0, 0, lambda. And this comes I times 1, 0, 0, 1, gives us this one. Lambda, 0, 0, lambda. Okay, this is a diagonal matrix, and that gives us 4 minus lambda, 2, 3, and 5 minus lambda. And I'm interested in the determinant of this matrix. And the determinant of that matrix gives us this equation, lambda square minus 9 times lambda plus 14. That will be equal to 0. And these are the lambda values which provide this equation. So the lambda values are 7 and 2. Okay, so these are called eigenvalues or characteristic roots. They are roots because they are coming from the roots of a quadratic equation. Okay, eigenvalues here. There are 2 eigenvalues. One is 7, the other is 2. These are also called characteristic roots. This is because different researchers, they made contributions in different times and they gave somehow different names. Sometimes you hear this latent roots as well. And there are many names used, and these are the ones which are the most used, let me say. Eigenvalues, characteristic roots, latent roots, and such things. So here, these are the ones. And but our job does not stop there. We want to also find these eigenvectors. Now, when you look at these eigenvalues, what do you see? They are real, okay? And they are both different than each other, in the sense that because when they are equal to each other, we have some other outcomes from that. They are different, and both of them, they are real values, because eigen values, they are not especially real. Sometimes you would get imaginary numbers there or complex numbers. We would use these eigenvalues when we do our especially dynamic analysis. And then sometimes we would get complex ones. Sometimes they would be equal to each other. This is perfect because this would let us to obtain some kind of diagonal matrices, and we will discuss about that. Characteristic vectors or eigenvectors. How do I find them? Basically, what I do, I just have just found, what did I find here? 2 and 7. Take eigenvalue 2 and just substitute it into this matrix, A minus lambda times I matrix. And I get these 2 equations, okay? And these 2 equations, they imply that x1 basically is a linear function of x2. It takes this form. And now, help me. How many values there are with this property? Kaç tane değer bulabilirim böyle? Yani x1 eşittir eksi x2 diyor. X1 ve x2 reel sayılar olmak üzere kaç tane değer bulabilirim bu eşitliğin tuttuğu?
Sonsuz.
Sonsuz tane değer bulabilirim gerçekten. İşte x2'ye 0 derim. Yani şöyle olur. Eğer buraya x1 yazarsam, x2 yazarsam 0, 0, 1, eksi 1, 2, işte diyelim ki eksi 2. So this is basically what kind of a line this is, or I can write it in this way as well, x2 being x minus 1. It is something like this. It's a line with this property. This is 0, so here let it be x1, let this be x2. It is such a line, and there are infinitely many values over that line. All the values over that red line are the values which are acceptable. And in order to somehow, in order to choose something, not to have these infinitely many solutions, generally we impose this condition. X1 square plus x2 square is equal to 1. What does it tell us, this one?
We are normalizing the function because we need to identity, birim uzunluk.
Evet, evet. We want to have a unit length, a vector with a length of 1. We impose this condition, okay? And this condition helps us to reduce, instead of that there are infinitely many numbers, and then it helps us to reduce the number of x1, x2 values, and so that, and then also it helps us, actually, we will see it when we go to orthogonality, to obtain certain characteristics, okay? And when we impose this condition as well, okay, so that we make the length of the vectors, the vectors, sorry, to be 1, it somehow shrinks the space of eigenvalues. Okay, we want to have several, not 10,000. And in this sense, what we find this one, x1 being this one, okay, minus 1 over square root of 2, one of them, and the other being again minus 1 over square root of 2. Okay, and we look at for the when this eigenvalue is equal to, bunlardan bir tanesi herhalde şu şekilde olacak. Substitution of the characteristic vectors yields this one. Okay. Now we take the other eigenvalue. We just impose the same condition that x1 square plus x2 square is equal to 1. And then when we do that, we end up with these values. And we will see later how we will use these eigenvectors and eigenvalues, how we will use them to turn them into some diagonal matrices. But before that, we need some terms, we need some kind of other concepts, and that's called similarity transformation. What we do here, we try to find similar matrices. Bunu sürekli yapıyoruz aslında, değil mi? Şöyle bir işlem düşünün. Desem ki ben size şunu çözün. Yani yaptığımız şeyin aslında bundan bir farkı yok. Matrislerde de bunu yapıyoruz. Bunu çözün desem size. Artı diyeyim ki işte 5. Ne yaparsınız? Şöyle 0 diyeyim. Ya da şuraya bir eksik koyayım ki çözülmeyecek. Ne yaparsınız? Böyle bir size denklem versem ne yaparsınız? Bunu böyle çözmeye kalkmazsınız, değil mi?
Hocam x üzeri 4'e mesela a deyip a kare eksi a artı 5 şeklinde
Aynen.
yazarak daha simple bir halde görebiliriz belki.
Aynen. Teşekkürler. Yani buna mesela a desem, o zaman bu ne oluyor? A kare eksi a artı 5. Bunu çözebilirim değil mi? Burada yaptığımız işlemde tamamen bu. Matrisleri alacağım. Çok genel halleriyle ele alacağım. Fakat onlarla hiç uğraşmak istemeyeceğim. Yani o en genel halleriyle hiç uğraşmak istemeyeceğim. Onları belli bir değişikliğe tabi tutacağım. Transformasyona tabi tutacağım. Ve o transformasyondan elde ettiğim sonuçları yani kullanaraktan tekrar yine orijinal matrislere döneceğim. Yani burada yaptığım işlemlerin şundan hiçbir farkı yok. So I call it as similar matrices. Okay, so I want to make such transformations so that, like here, I turn this equation into a form which I can work with. Okay, then if I find, for example, a values, let it be star, and I know that it is, I will just apply the same logic here. It is sorry, I know that it is equal to x over 4, and from 1 I would go to the other, and this and that. The same logic would be applied here in terms of matrices. I would simplify, or I would try to turn those matrices, complicated matrices, into simple forms so that I can work with them and obtain outcomes easily rather than with big difficulty. So here, for that, I have these similar matrices. Take again, these are all square matrices. They are all in general n by n matrices, right? And then here there is matrix A, and there is matrix B. Okay, these are the matrices. And what do I say that B is similar to A if this holds? Okay, and C is here again n by n matrix, and it's a non-singular matrix. It means that all the rows and columns are linearly independent. Okay, then I say that from I can, by using this C, I can obtain from A, B, and then in a similar way, from B, I can obtain A. Okay? Birinden diğerine gidebiliyorum. Bu C'yi kullanarak A'dan B'yi elde ediyorum. Yine C'yi kullanarak B'den A'yı elde ediyorum. Okay, so that I can transform one into the other way, and if I can do that, I call these matrices as similar matrices. Okay, and in that case, I say that if I multiply B, for example, with Y in this way, lambda being a scalar, but B being a matrix, if I multiply both B and lambda with this Y vector, okay, and then I know what B is C inverse of C times A times C, and then here I end up with this expression where I end up with A, okay. And we will see this as well with an example. And in that sense, I just use this transformation that X, I can go from Y to X, from X to Y in this way. And this is what we do in terms of similar matrices. And if the matrices, if A and B are similar, then A and B have the same characteristic equation. This is the characteristic equation associated with B, and this is the characteristic equation associated with A. And all these, they come, if you analyze it, they all come, the operations, how we get how we go from this to B expression to A expression, you can follow them. And it tells us that both A and B, they would have the same eigenvalues because they would have the same characteristic equations. So here there is a note: similarity transformations preserve eigenvalues while they do not preserve eigenvectors. Eigenvectors are still easily recovered. Okay, how they are recovered? They are recovered in this way: that that one vector will be multiple time of the other. And this is the punchline. This is what we are interested. A diagonalizable matrix. A matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Okay, this means that there exists a P matrix such that if I multiply inverse of P with A and that expression with P, I obtain D, and D is a diagonal matrix. Okay, eigenvalues of a diagonal matrix are its diagonal entries, and eigenvectors are corresponding columns of an identity matrix. Diagonal form is desirable target in simplifying eigenvalue problems for general matrices by similarity transformations. But some matrices cannot be transformed into diagonal form by similarity transformation. Okay, now we have some theorems on these matrices, and we check whether we can obtain such forms like here by using A, whether I can get to D and use D and then get back to A. This is the aim. The theorem here tells us that the n by n matrix A is diagonalizable if and only if there is a set of n linearly independent vectors, each of which is a characteristic vector of A. Okay, so it says that the characteristic vectors, they have to be linearly independent from each other. Now we look at the condition where the independence of characteristic vectors holds. Now here we have the theorem. Suppose there are k eigenvalues or characteristic roots of an n by n matrix, no two of which are the same, and let x be the characteristic vector associated with xi be the characteristic vector associated with lambda I, then these characteristic vectors, they are linearly independent. It says that assume that we have this simple word of 2 dimensions, and in this case assume that we obtain eigenvalues, let's say lambda 1 and lambda 2, okay, and we say that they should not be equal to each other. They are called distinct. The eigenvalues, they have to be distinct. If that is the case, then the characteristic vectors that we would obtain by imposing those conditions would be linearly independent vectors. And if they are linearly independent vectors, then that A matrix, this matrix, from this A matrix, I will produce another matrix, which is D matrix as here, and that matrix will be a diagonal matrix, okay? And I would work with that diagonal matrix, and all the outcomes will be transformed in terms of A matrix later. So here we have these distinct characteristic roots. If you have a system with, let's say, 1, 1, 1, 2, 1, 3, 3 by 3, so you have 3 variables, what happens? Maybe you have assume that we have lambda 1, lambda 2, and lambda 3 vectors. This says that to obtain a diagonal matrix, none of these, they have to be equal to each other. Lambda 1 is different than lambda 2. Lambda 1 is different than lambda 3, and lambda 2 and lambda 3, they are different, so that they are all distinct eigenvalues. Then we say that if an n by n matrix A has n distinct characteristic roots or eigenvalues, then it is diagonalizable. Okay? And when we look at the matrices with distinct real eigenvalues, if we don't have these distinct eigenvalues, what will we do? Ne yaparız? Eğer değilse aldık işte A matrisini, baktık bu değerlere, karakteristik değerlere baktık ve mesela burada olduğu gibi 1 ile 2 birbirine eşit çıktı. Hadi üçüncüsü farklı bir şey oldu. Ne yapabiliriz o zaman? Matrisi çöpe mi atarız?
Birini diğeri cinsinden yazıp silebilir miyiz? Ya da silebilir miyiz?
Yani bence sadece şunu söyleyebiliriz. Buradaki yöntemler çalışmaz. Başka bir şeylerle uğraşmamız gerekir. Onlarla da uğraşıyorlar. Mesela matrisin diyorlar ki işte şöyle bir diagonal olsun. Çünkü bu koşullar çok nasıl desem hani katı koşullar. Bu diagonal element olsun. Diyorlar ki mesela bunlar aşağıdakiler, yani diagonal olmayan elementler 0 olsun. Ya da yukarıdakiler 0 olsun. Yani bir şekilde başka metotlarla sorununu çözmeye çalışıyorlar. Ama eğer tabii şu anda biz hani onların içine girecek değiliz. Ama tutmazsa yani demektir ki burada yaptığımız şeyler çalışmayacak. Başka yöntemlerle çalışmamız gerekecek. Böyle matrix decomposition diye bir alan var. Orada o olmazsa bu olmazsa bu diyerekten böyle değişik yöntemleri sürekli olarak gösteriyorlar. Yani hiçbir şey yapamıyoruz anlamına gelmiyor. Sadece buradaki yöntemleri kullanamıyoruz. Buradaki yöntemlerle bir sonuç elde edemiyoruz. Ama buradakiler, yani bu istediğimiz şeyi bulabiliyorsak yaşadık. Tamam, buradaki yöntemlerle işlemlerimizi yapacağız demektir. So matrices with n distinct real eigenvalues. Again, we have the square matrix, and they are distinct and real. This is important, real, because when they become complex, the complex world is complex on its own. We are able to write this equation, okay, and then you will see this with examples. Look here how I create this diagonal matrix, right? From these, I will show you with an example here rather than going over those notations. Now we have this square matrix, okay, and we want to have the eigenvalues, okay. What are the eigenvalues here? 3 and minus 1, okay. It's 3, the other is minus 1. They are real, and both of them are distinct, because lambda 1 is not equal to lambda 1, which is equal to 3, is not equal to lambda 2, which is equal to minus 1. Are we lucky? We are. It means that we will be able to obtain a diagonal matrix from this A matrix, and that matrix will help us to work with certain operations. Yani hem bu karakteristik değerler hem reel sayılardan oluşuyor her iki karakteristik değer için, hem de birbirinden farklı. Burada dikkat etmemiz gereken şey farklı olmaları. Farklı oldukları yani eşit oldukları anda başımız belaya giriyor. Yani buradaki yöntem çalışmayacak. Başka işlerle uğraşmamız gerekecek. Okay, what we do here, we just take these, put 3 into the equation that we started with, and put minus 1 into the equation that we started with, and obtain those. Like here, we have this one, x1 being equal to x2. This happens when the eigenvalue, did I say 1 for that? Yes. when eigenvalue is 3, we get this expression. And immediately we put this restriction, and this restriction is important for us to get the result which we want. And we say that x1 square plus x2 square is equal to 0, so that I'm dealing with a kind of a unit vector. And if I do that, I obtain these values, which are basically 5 divided by 26 and 1 divided by square root of 26. One eigenvector is here. And now I just repeat the same procedure when this eigenvalue is equal to -1. Then I obtain this equation, x1 equal to x2. And again, I impose the same restriction, x1 square is equal to x2 square. If I impose that restriction, these are the values of the eigenvectors, 1 over square root of 2, 1 over square root of 2 again. Now here, what do I do? In the first column is the eigenvector, which is associated with 3 and the eigenvalue 3. And this is the second column is the eigenvector, which is associated with the column where eigenvalue took the value of -1, right? And I do here take the inverse. So I formed a matrix, right? And the matrix basically is composed of the eigenvectors of those eigenvalues associated with those eigenvalues. And then I take here the inverse of that U matrix, okay? It's a basically matrix of eigenvectors. Now, what can you say about these eigenvectors? What can you say about these eigenvectors?
It's equal to A matrix.
These columns, are they linearly dependent?
Independent.
Independent. En başta bunu söyledik. Eğer dedik ki reel değerleri olan ve birbirinden farklı karakteristik değerleri bulursak onlardan yaratacağımız bu karakteristik vektörler birbirinden doğrusal olarak bağımsız olacak. Yani sütun, birinci sütun burada, ikinci sütundaki birinci sütundaki vektör, ikinci sütundaki vektör birbirinde, bunlar doğrusal olarak birbirinden bağımsızlar. Bu ne anlama geliyor? This matrix here, basically matrix of eigenvectors, can be invertible. So it's a non-singular matrix. And it means that I can find the inverse of it. And this is the inverse of this U matrix as U minus 1. Okay, this is the inverse. And now look at here. It says that if I multiply this U minus 1, which is the inverse of U, with A, the matrix that I started with, and then U, it would give me this matrix. Okay, this is a diagonal matrix. And if you look at the elements of the diagonal matrix, what are the diagonal elements for this matrix? Bu kadar uğraştım, bu vektörleri buldum, çarptım falan. Ne çıktı en sonunda? Bu işlemi gerçekleştirdiğimde. Bunlar neler? These are eigenvalues. Okay, so here, immediately when I know that eigenvalues are real and they are distinct, I know that I will get this result. Okay, and the nice thing here, there is one operation. It's so easy to find the fourth degree of this. And look at what is fourth degree. Yani bunun 4. derecesine bakarsam, yani şöyle düşüneceğiz. Matrisi 4 kere birbiriyle yani power 4 habire çarpıyorum. Ne görüyoruz burada? Hemen çok şık bir sonuç var. Neye eşit aslında? Yapmam gereken tek işlem o diagonal üzerindeki elemanların 4. kuvvetini almak. 100. kuvvetini almak istersem 100. kuvvetini almak istersem
Diagonal üzerindeki elementlerin 100. kuvvetini alırız o zaman.
evet, aynen öyle. Yani o işlem o kadar basit hale geldi ki. And then here, how can I find the question here, if I'm interested in finding this, okay? What can I do? I just apply this operation, right? And then easily I obtain the power, 4th power of A as well. Okay, this is, I mean, we would not be very much going after these things. There are parts of, I mean, some parts of science, let's say, they deal with such things. This is just to show you how easy to do certain operations after we basically obtain a diagonal matrix. And we transform one into the other. From, let's say, diagonal matrix D, we are able to go from D to A. Okay, all these results that apply to D can be transformed also, all those outcomes can be transformed into A as well, easily, so that we are not dealing with this very cumbersome operations. Bir sorunuz var mı? Yok. Şimdi şöyle bir şey. We will start something called quadratic forms. Okay, and I wouldn't make it too long. I will try to talk about it. Yani şöyle söyleyeyim, 1 saatin üzerine çıkmamaya çalışacağım. Fakat buna başlayacağız. Bu optimizasyon için en önemli konulardan biri. Bundan önce de bir şöyle 5-10 dakika bir ara verelim. 10 dakika sonra buradayız. Okey, olur mu?
Evet.
Tamam, 10 dakika sonra görüşüyoruz o zaman. Yalnız ben bunu gitmeden size bir yollayayım. Çünkü başka bir dokümana geçeceğim.